Okay, hi everyone. Good morning.
Morning.
It's very nice to see you all. Thank you for coming. So last week, I saw you last Saturday. I gave a very broad overview. As a disclaimer, my week, I saw you guys on Saturday. On Sunday, I traveled to a conference where I was all week, and I had been asked to, in the middle of the week, give a sort of big talk that I had been, it's a sort of talk where one is honored to be asked to give the talk, but also somewhat terrified. A bit like this, except with this talk at this conference, many of the audience were people who in a couple years I'm going to ask to be giving me a job, so even higher stakes. But it went well, thankfully. But then I flew back from the conference last night. My plane arrived around 1 a.m. So
We're so pleased you survived to be with us this morning.
thank you. Oh, it was pretty hairy. I was there's this famous Institute's Center for Physics in Aspen. There was a big snowstorm. We only barely made it out. But yes, I'm glad to be here. That is to say, okay. So this week. Well, good. What do I want to say? For the first lecture last week, you experienced it. You know, I sort of written it as a 1-hour speech. I'd like my plan this week is to be a little less structured, more improvisational, and correspondingly more interactive. So please, if you have questions, raise your hand. I'll try to get to things if anything is confusing or anything. And I'll also rely on a few videos you'll see. There's a topic that's good for, that animations are good for it, so hopefully that will help explain. Good, but the point now, today's topic is to go to the atomic scale, and to understand at some level, at beginning level, the structure of matter, and we'll find that we have to learn quantum mechanics to properly understand how things work at that scale. Let me write the scale. In fact, so the size of the atom, we're going to be at roughly the atomic scale, is roughly, how big should I write? Probably bigger than that.
Yes.
Perfect. Is roughly 10 to the minus 10 meters. And someone kindly pointed out to me, I without thinking last week, also I used scientific notation. That's what this is to talk about numbers. So let me just briefly say, so a number like 10 to the minus 10 meters is really, so a decimal place, and let me see if I can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. Okay, this is the sort of atomic scale given by what's known as the Bohr radius, roughly the size of the atom. Okay, so I wanted to clear up if that had confused people last time, and probably I'm just so in the habit of talking about numbers this way. I'll continue to do that. Ask questions if anything is unclear. Good. Okay, so we're going to the atomic scale. Slightly before we get there, sort of in the theme of zooming down, I want to briefly pause.
Is this the distance between atoms, or is it the size of the atom?
The size.
It's
about the same.
It is about the same, indeed. They're both controlled by the quantum electromagnetic interaction. So at the level of precision I'm working, indeed, they're both around 10 to the minus 10. That's a great question. Okay, I wanted to briefly pause at sort of the cellular scale before we get down really to 10 to the minus 10. My last biology class that I took was in high school,
Ouch.
and so when I learned about cells, it was from some handouts with some photocopied black and white picture of a cell. Perhaps your experience is familiar. I wanted to play. I only learned a couple years ago that we can now do. And I think I already opened this in a different tab. We can now do real-time, high-definition microscopy. So certainly when I learned about cells, everything was very abstract. Didn't really feel, it wasn't really palpable. And that was perhaps why I was able to hold on to some of my confusions about how life worked. Sorry, I'm just reminding myself what parts of this I want to play. So I just want to briefly show some images because I think, well, my opinion is that it's really remarkable that we can see this.
Analogous parts, but their lives and physical appearance can appear vastly different when compared to each other.
Maybe I shouldn't have
The
any
bodies of
the sound.
multicellular organisms.
But indeed, you can just some of this is maybe not the right. Nope. Sorry, let me try to get the lights. Oh, that's not the right one either. At some point last week, I had figured this out, right? No, is Mary? Okay. All right. Well, it's not biggest deal, although I think you can't see. What? Okay. Well, a little bit dark. Okay. Good. Thank you. Let me. Indeed. Let me play a little bit of this again. It just people talk about life in very mystical terms often. Certainly, that was how I learned and thought about it. But you can just see this. And indeed, we're down at very small scales here. You have some cells that are manifestly alive. They're doing things, but at the same time, it's just chemistry. It's some fantastic arrangement of chemistry that allows this complex emergent behavior. But nonetheless, it's some physical system. You can see it moving, responding to things, right? Some more something. Of course, there's an enormous range of sorts of microscopic of sorts of cells, of sorts of organisms, bacteria. But at the end of the day, it's physical, and you can understand, you can see at an incredibly small scale what's going on. Here they're highlighting some vacuole that the cell is using to expel some chemicals. Good. I think there was one further clip I wanted to highlight here. I highly recommend this channel called Journey to the Microcosmos, just full of absolutely remarkable high-definition videos of the cellular world. So I highly recommend it. They're highlighting something about how this molecule, this organism works. Okay, all right, but I can let you investigate that further during the week. Good. And they have some great videos about there was a question last week about the difference between living and non-living matter. There's some great videos about what death looks like on the cellular scale, but maybe I should let you look at that later.
Thanks to
Oh God. Okay. Good. And again, before zooming down, just briefly reminding you that we understood into the 1800s lots of chemistry by chemists, by physicists, understanding how these molecules can interact and can be rearranged to do all of the. Oh yeah, we had. Yeah, can we make sure that this light stays? Oh, wonderful. That's perfect. Wonderful. Thank you so much, Mary. Good. Good. And of course, we can understand lots of processes that we care about, respiration, or something like fermentation maybe is dear to your heart, in terms of how molecules are rearranged chemically. Good. But just briefly pausing there, we want to get down to the atomic scale. And as I briefly mentioned last week, in the late 1800s, it had been realized that if you put some large electric field across two metal plates, they produced something. These were known as cathode rays. You could see them producing some sort of molecules. J.J. Thomson's insight was to, have a nice experimental setup where you could put a transverse electric field to affect the output, whatever was being outputted, whatever these cathode rays were. And he found that the cathode rays produced by this large electric field between these two metal plates were producing some sort of electrically charged particle. It responded, it was deflected in an electric field. And the interpretation of this is that there is some sort of negative component of matter, of the atom, that is relatively easily stripped off. Okay? Of course, maybe I should mention more practically, cathode ray tubes powered your televisions for many decades. Yes?
As a particle, does the electron have a definable size that's analogous to that Bohr radius size you give?
That's a good question. So when we talk about fundamental particles, in fact, they will have no size. Zero. The electron has zero radius. Fundamental particles are in some sense, infinitesimal. That's a good question, and we'll see that we'll discuss that more as we go down further in scale.
And can you have more than one at the same point then?
Can you have more than one at the same point? That's a very good question.
I might add, it's akin to the question of how many angels can dance on the heaven.
Except it's not, because this is a well-defined physical question, and in fact, it's a good question. There's a good answer to it. Okay, we're jumping a little bit ahead, but in fact, the sort of particles that electrons are, something known as fermions, means that you cannot have two of the same particle in exactly the same point. But for in fact, this is not true of all particles. Light photons are, which we'll get to, are a different sort of particle that in fact can be in the same place as each other. Bosons. So there is. It's a good question, and in fact, the answer is it's a well-defined physical thing that depends on which sort of particle you have. Hopefully, we'll get to that. Yes.
Could you back up just one short step?
Uh-huh.
I have a hard time making the move from cells as complete living things, euglena, to the point at which now we're looking at the components of atoms.
Yes.
Could you fill that little spot in just a second? Or if you're going to do it later on, then I'll be quiet.
it's another good question. Well, to some extent, we don't understand fully the map. We know a lot about how cells work. There's some fantastic work being done a block that way on campus. We don't understand everything, but you can zoom in further on a cell and find that what do I want to draw? You can I think I showed a picture last week. You can find if you zoom in on some cell maybe has lots of things going on. If you zoom in on say the cell membrane, which I mentioned last, but of course is a very important part, sort of defines what is and isn't the cell. You can find that it has some structure I'm not a biochemist, I should say, but it has some particular structure. In fact, maybe I can even get up the picture from last time. I was zooming in too much this time. Yeah, indeed. Good. Okay. This was going to be the picture I drew. Indeed. So you're right. I'm definitely skipping a lot, but we understand the cell in terms of various structures, various complex proteins that make it up. Biochemists have done fantastic work in understanding the molecular structure of different parts of cells. Of course, so this is DNA, which there's been lots and lots of fantastic work understanding how it works. And indeed, the whatever magic you'd like to assign to life, it comes out of some complex emergent behavior from interactions between molecules, some relatively complex arrangements of atoms in this nice cellular environment. Sorry, that was a bit rambling.
That's okay, you just keep on going.
Okay, thank you. Good. And indeed, this is a fantastic area of inquiry. I'm sorry I don't have a biochemist on hand to answer all of the questions. It's something I'd like to learn more, understand more as well. Okay, but all right. So we found that matter contains some particles with negative charges that are relatively easily taken off, stripped off of a material. Now, what about the positive charge? We know that atoms are overall electrically neutral. We found this negative charge that we can easily take off. There needs to be some sort of positive charge. And for a long time, or for some time, people, a popular theory is what's known as the plum pudding model, that you imagined there was some large blob of positive charge, and the negative charges, what we'll find are electrons, were sort of randomly distributed throughout. I think the analogy is as raisins in a plum pudding, although this is a British type of pudding, so I think the analogy makes more sense over there. But in any case, as mentioned last week, in order to learn more about the structure of the atom, what the great physicist Rutherford suggested was to do some more scattering experiments. And this is going to be a very important sort of concept as we understand matter at smaller and smaller scales. So here, you can imagine what we're doing here is seeing some sort of classical deflection of this cathode ray, really this electron beam, to understand the interactions of the electrons. Here we want to do even a more short distance sort of scattering. What Rutherford suggested is that we take some gold foil, some thin sheet of gold, which is a relatively heavy element, and you shoot, they call them alpha particles. What these really are helium ions. So helium is a light element, and you take off the electrons, like we saw before, relatively easily done. And Rutherford suggested probing the structure of the atom by shooting some smaller elements at it. And this is going to be a very important sort of principle. And the idea is that different physical pictures of matter at a very small scale of what the atom looks like lead to different sorts of predictions for this scattering experiment. And so by setting up this scattering experiment and measuring things very carefully, you can understand between different arrangements of matter, different theories for what physics looks like at very small scale, without being able to really zoom in or look in visible light the way we could look at the cell. Okay, so what did they find, or what did they expect? So if this plum pudding model had been correct, then most of the time the helium ions, the alpha particles, they might pass through some atom, but the positive and negative charges are sort of distributed on average equally around roughly this 10 to the minus 10 meter scale. So some sort of average arrangement where if a helium ion were to enter, it would see roughly the same amount of of negative and positive charges, and you would not expect much deflection. Okay. Whereas what was actually found is that indeed many of the alpha particles went straight through the gold foil, but there were some cases where the helium ions bounced back at some large angle. You had some large amount of scattering. And the correct interpretation, I have a, okay. The correct interpretation is that rather than there being some large sphere of positive charge, in fact, the positive charge is concentrated in some very small region at the center of the atom. And most of the time, indeed, your helium ion goes near the atom, or through the atom, and it can see both the negative and positive charges, and so it doesn't get deflected very much. But every once in a while, your helium ion, by chance, passes very close to this small region in the center of the atom where the positive charge is concentrated, and so it can have, it sees really just the positive charge and is insensitive to the negative charges that are farther out, and so gets some very large kick from the electromagnetic interaction. You find these very large deflections. Okay, so these were these famous experiments at the beginning of the 20th century.
Question.
Yeah, please.
When you're sending the alpha particles through the metal, is there an interaction with the electrons in these experiments? The alpha particle
Yeah.
interacting with the electron.
Yes, good. Good. And I've just remembered I should be repeating questions, but if I don't do that in the future, tell me. Good. So the question is about whether these incoming alpha particles interact with the electrons, and the answer is that indeed they interact both with the electrons and the protons, but it turns out it turns out that the interesting results in this experiment are from the interactions with the the nucleus, the positively charged sort of core of the atom. Indeed, there are interactions both with electrons and with the nucleus, but as long as you don't get too close to the nucleus, then roughly your incoming particle can see both the electrons and the nucleus. It can see both the positive and negative charges, and so they add up to something neutral. And so you don't see much deflection. The interesting deflection comes from this positive charge localized in the center of the atom. Good question. Yes.
So I've always found myself interested in the fundamental concepts and definitions. And in fact, once when I heard a lecture by a distinguished physicist of this university, whose name escapes me, but he was in charge of a huge consortium of South Pole experiments.
Cosmologist, sure.
He was talking about his work, and I asked him the question, what is charge? And his answer was, physicists are asking themselves the same questions. So is there is that an irreducible concept of a property of matter, or is there some way you could define it in layman's terms?
Good. So the question is about the concept of charge. I don't entirely. I'm not really sure what this other physicist had in mind with their answer. Indeed, at a fundamental level, and we'll get to this in the next couple lectures, but at a fundamental level, what we have are particles that interact with each other. And charge is one property that particles can have that controls how they interact with other particles. It's entirely a well-defined thing. This is a feature of our deepest theories of nature. Sort of the way that you define what physics in our universe looks like involves which sort of charges different particles have. So yeah, it's a well-defined fundamental concept. I wouldn't say that we're confused about it. I think it should be, and maybe we'll get to this if I talk about quantum field theory. It should be it is a fundamental feature of our best theories of how the universe looks at very small scales. But maybe we can talk more offline.
Is it a property, or is it something that it exists? Does the charge exist without being part of the particle?
No, it's good.
Or it has to be part of a particle?
Good. Electric charge is a property of a particle.
It's a property.
That's right.
It is not an entity by itself.
That's correct. It's electric charge is something that is associated to particles. That's absolutely right. Right. I think there was a question in the back, although I should be a bit careful not to. Yeah.
Real quick.
Yes.
Does the ion particle have a charge?
Yes.
Indeed. Yes. Sorry. Thank you. I should have said that. Yeah. So helium ions are helium atoms, so the atom is neutral. A helium ion, you take the electrons off, so what's left is a net +2 charge. Thank you. That's a good, very good question. I should have said. Okay, good. But we're still we haven't gotten to the meat of things yet. Well, so what the hell is actually going on, right? How does this? I can draw this picture. Maybe I can tell you the arrangement of things has to be this way. But why? What's actually going on? And this was very confusing. What you might think is, okay, from classical physics, from Newton, we know how to write down the gravitational force. You have G is, well, we call it Newton's constant. It controls the size, how big the gravitational force is. You have, if I'm thinking about the force between the Earth and the Sun, you have the masses of the Sun and the Earth. It goes down as 1 over distance r, or distance squared that is, r squared. So we know that this gives some circular orbits of the Earth around the Sun. And in fact, classically, you can write down the force between electrically charged particles, and this takes much the same form. K here, again, controls the size of the strength of the electromagnetic interaction. Here we have the charges that control again, the size for these particular, how much these particular particles interact. It's a 1 on r squared. So your natural picture, if you're a classical physicist in the 1800s, is that, okay, maybe the electron orbits the proton just like the Earth orbits the Sun. This seems to be naively what this picture of the atom might be telling you. However, that can't be correct. Just from classical electromagnetism, the fantastic physicist Maxwell had understood a first sort of complete iteration of electromagnetism in the 1860s. From electromagnetism, charges which are accelerated, which move in something other than a straight line, charges which are accelerated radiate. That means they lose energy. You can sort of think of, as an analogy, if you spin a fan, it gives off some sound waves that likewise carry energy. So from classical electromagnetism, if the electron orbited the proton, we're really going in some circles around the proton, it would need to give off energy. And in fact, you can calculate that this would result in the decay of matter in something like 10 to the minus 11 seconds. So something is not right with this picture. We need some sort of new physical principle. The answer will be quantum mechanics, but before I get there, let me talk about a parallel sort of topic. Good, so that is waves. Okay, so waves are some sort of propagating disturbance. Maybe I won't move that. Good. So waves are a very general phenomena. Some sort of propagating disturbance. You can have, and you can rely very much on your sort of physical intuition here. You can have some wave traveling with some speed. That's a wave. Very often we'll talk about some periodic waves. Is this too low? Is this roughly visible? Okay. Very often we'll talk about some sort of periodic waves that repeat in time. These have, you can associate to these a wavelength. I should have switched to a different color. You can associate to these a wavelength, sort of the distance between peaks and troughs, often referred to with the letter lambda, or similarly, inversely, you can think of the frequency of these waves, how often they repeat, often f. These two are related by the speed of the wave. Okay, some sort of periodic disturbance, a very general phenomenon. And in fact, as I alluded to, sound, all sound, what you're hearing now, is some sort of waves of pressure of the air. Let me play briefly a thing. Maybe I don't need it to hear, but just a brief animation. What's happening with all sound is that you have some longitudinal waves, some areas in the air of compression and rarefaction, where things are denser or not, and this is how we hear things. This is some additional information about the world that's out there in nature that our bodies have learned how to take advantage of. And indeed, maybe I should just replay.
Are these sound wave, the rarification, and these are sound wave, or the sound wave are pressure?
Well, I think you said the same thing twice.
No, the rarification,
Yes.
they say it is air particles
Indeed.
that can align. You have an area where air particles are less dense,
Yes,
and areas where they are more higher density.
that's right.
Okay, this is not a pressure wave.
Well, good. No, sorry. So
This is really kind of.
I mean, so you can think of it as so. The question I think is about pressure versus density. You're pointing out that really the words I've said are about density, but the ideal gas law. I'm not a thermodynamicist, but the ideal gas law, to wit, sort of the ideal gas law relates the pressure and the density. So indeed, you can think of them either as density waves or as pressure waves.
It is RT, not K.
I think this is different units, right? And RT, these are maybe the chemist units. I'm using the thermodynamic, or maybe the statistical mechanicians units. But either way, indeed, I think yes.
You know, sound wave was described as a kind of each air molecule, okay, kind of is a sphere, and you have all these spheres next to each other, and when from one side there is a pressure coming, and the pressure wave goes through them, so they kind of bump into each other.
Indeed.
And that's how it passes.
I agree.
But if a twine is excited, it really disturbs the molecules of the air. It rearranges the molecules of the air, and so these molecules get some kinetic energy that eventually the kinetic energy will be converted to a pressure wave. So, but the kinetic energy has not to be confused with this, with the pressure, okay?
Sure. Maybe we can talk more about the details. Indeed, no. I appreciate the advanced questions. I do want to make sure I get through. We haven't even gotten to quantum mechanics yet, so I want to get through things. All right, good. So this is just you can visualize these sound waves in some nice ways with some small particles on plates, and then you can really see these small particles arrange themselves via some according to these pressure waves. A way to visualize it. Let me skip ahead a bit. Now, waves are important because waves can interfere with each other. When you have, how do I want to manage this? Okay, maybe I erase the pore radius. Good. So for a long, the reason I've switched to waves is because for many centuries, so there was an argument about the nature of light, whether light was a particle or a wave. And we'll see this is very related to the structure of the atom. Now waves can interfere with each other. Unlike, so what I mean by that is if you have this is a wave. If you have two waves and they are in phase, meaning the peaks and troughs of the two waves line up, then these constructively interfere and you end up with a wave with a larger amplitude. The peak of each lines up and you have some even larger wave in the end. This is probably roughly familiar from your experience on Lake Michigan or something.
Sure.
And indeed, on the other hand, waves can not only constructively interfere, but they can destructively interfere. If you line up your waves, misalign your waves maybe, so that the peak of one wave overlaps with the trough of another, then in fact you can cancel out wholly or partially, depending on how well aligned your waves are. You can cancel out these peaks. So waves have some sort of interference effects. Let me briefly show this in water. I'm going to skip to something like this. Okay, what they have here is a water tank where they are periodically dipping something in to create waves, and you see this sort of interference pattern. Here we're seeing the waves through the water waves through how they affect light, but indeed this, we call it in English an interference pattern, is the result of different waves aligning or anti-aligning as they overlap with each other, and as a result producing interference. Okay, this is maybe familiar from water waves. Indeed, if you have two waves that cross each other, then you perhaps have seen that you get...
In water, there is sound wave and there are ripples.
Uh-huh.
Are they different from each other or they are the same?
That's a good question. So the question is about the difference between sound waves and water waves. And indeed, this is... perfect. Indeed, sound waves, these pressure waves, are longitudinal waves. As we talked about, compression and rarefaction, the water waves are transverse waves. That is, the up and down motion of the wave the oscillatory motion of the wave is not in the same direction as the way the wave is moving. So they're related phenomena, but different.
Water ripples are not the sound wave in the water.
That's correct.
Okay.
That's correct. Yeah, there is a difference there. Good. Okay, but the point is that light is a wave. You've probably perhaps seen such a slide like this with light of different wavelengths, different sizes of lengths of these waves, along with different names we give it. Our vision works in a very small band where the wavelength is between something like 400 and 700 nanometers. Let me just emphasize that we have different words for these terms in English because we didn't, we named these things before we properly understood them. But radio waves are just light that has a very long wavelength, and we talk about them differently because depending on their wavelength, how it relates to, say, our size, they can have different behavior. Radio waves, because they have very long wavelength, can just pass through matter without us noticing. Of course, there are tons of radio waves going through all of our bodies at this moment. Whereas, on the other side, X-rays or gamma rays, very short wavelength, and so can interact with the matter in our body. Good, but we'd like to understand this precisely. And so what the physicist Young suggested doing, an experimental setup where he could study this precisely. Okay, and in fact I had drawn some poor versions of this. Maybe I should just show them in light of the time. Okay, so if what Young suggested, good. What Young suggested is what's known as the double slit experiment. Here first with one slit, the idea is I have some light source here. To be clear, good, I should be clear with what these drawings are. So I've been drawing these one-dimensional waves. Here I'm sort of switching to 2 dimensions, so you should imagine that what I'm drawing here are, you might say, the wave fronts, just the troughs of the wave. So I'm just, because I want to draw a 2-dimensional spatial picture, I have to just denote where the troughs are, or the peaks, either way. But the idea is, okay, if I have some light source and I pass it through, I aim it at some plate with a small slit cut in it. Now, when light goes through a slit, there's this phenomenon of diffraction, or the Huygens-Fresnel principle. It sources a new sort of circular light wave. So if you shine light through a single slit, you get, well, what you might expect. You find that you have one very bright spot, and the brightness dies off because, well, most of the light just goes straight through, but you can go angular as well. Good. But the surprise now is what happens, or the important point is what happens now when we have 2 slits. So when now I have 2 slits in my plate, the light passing through each slit creates comes out as a sort of circular wave, and we can understand from this that the light really is composed of waves that can superimpose. The light that comes through this one slit and through the other slit are in general out of phase. So there are some spots where they interfere constructively and you get a very large amplitude of light, you get some bright spot, but other points where they interfere destructively. You can think, for comparison, what you might expect if you shot tennis balls or something at such an experiment, right? If you were, rather than shining lights, you were shooting tennis balls, you'd expect some particles that don't superimpose, that can't add together to create some good. If you were just shooting tennis balls, then you'd expect 2 bright spots with 2 places where most of the tennis balls ended up. But in fact, we find this diffraction pattern, and I can show you some real result. I'm sorry, I haven't arranged to do the experiment here, but in any case, you find some interference pattern from the light from these 2 different slits interfering with each other. Okay, so light is a wave. Oh boy, good. The time. Okay, light's a wave, but so that seems to settle the matter. But then in the early 1900s, physicists did more precise experiments shining light on metal plates, and they found these surprising results. So given that we know that matter has some electrons, some negatively charged components that can be relatively easily stripped off, And given that light is a wave, and the energy in a wave is proportional to the amplitude of the wave, right? So just from the beach, of course, you know that a larger wave is can more easily knock you over. You think that if you take some light, and any source of light, and you shine enough of it on some piece of metal, then again, you think you can strip off these electrons. You can knock them off. But in fact, what was found is that whether or not you can take electrons with light off of some piece of metal depends on the frequency of light that you shine on it. If you have some relatively long wavelengths, so red or even longer wavelength light, and you shine it on a metal like potassium, then no matter how much you turn up your red flashlight, you won't get any electrons off. On the other hand, if you take a shorter wavelength of light, that green or blue light, you'll find that even with a small flashlight of this green light, you can shine it on a metal plate and electrons pop off. So this picture of light as just a classical wave where the energy carried by it is proportional to how much light you're shining on it, something is wrong, because you wouldn't expect this sort of frequency dependence. And in fact, it was Einstein in the work that won him his Nobel Prize who explained the photoelectric effect, or what this is, by saying that somehow, even though light is a wave, it must come in some sort of quantized units. The way to explain this must be that there are individual light particles as well.
This is Planck.
I think this is Einstein.
Einstein or Planck?
Planck got it slightly confused.
Yeah, so
Einstein's straight.
yeah, good. Planck had some earlier. So Planck was before Einstein. Had some very important in a more complete telling of the history of quantum mechanics. Indeed, Planck's work understanding blackbody radiation is incredibly important. But it was Einstein who explained the photoelectric effect by recognizing that this must mean light somehow came in units with some energy that was proportional to the frequency. H here is called Planck's constant. So Planck is certainly involved. But light must somehow come in some units, in some quantized units, even though it's a waves. And in fact, it's even more confusing because we know that electrons are particles, but in fact, electrons are waves as well. So with electrons, you can fire them at such a double slit experiment. You can put up the same double slit experiment. You can fire electrons one at a time now. And even though every single electron you detect it at one specific place, it's certainly a particle.
This passage has nothing to do with
when you do this experiment many times, you fire many electrons, you find that the electrons end up in some sort of interference pattern. Again, some bands where the electron is interfering constructively or destructively. But this is very puzzling because here you're really shooting one electron at a time. So how the question is how does the electron know to interfere with itself? Somehow each individual electron is again, just like your wave of light went through both and interfered, even somehow an individual electron is interfering with itself to bear out the same sort of interference pattern. So this is very confusing. Classically, it's not clear how to make sense of this. But the answer, and the other one has disappeared now. The answer is quantum mechanics, okay, perfect, good. So somehow we saw photons have this wave behavior, but they also have this particle behavior. We see also, even though electrons are clearly particles, you can talk about one of them, they somehow have this wave behavior. And the answer is quantum mechanics. In fact, at some deep level, everything is waves. But what's remarkable about quantum mechanics as a physical theory is that even though everything is fundamentally some sort of wave, quantum mechanical waves, as opposed to classical waves, quantum mechanical waves can have particle properties. So what Schrödinger wrote down, this Schrödinger equation, is a wave equation for something called the wave function. And part of what's so confusing about, part of why quantum mechanics works out in such a special way is that, in fact, you might be tempted to say, okay, I'll write down some sort of equation for the probability of finding an electron at a particular place at a particular time. In fact, what quantum mechanics demands is that the thing that obeys the wave function is not, the thing that acts as a wave is not the probability itself, but it's a wave function that then Born taught us is related to the probability as, the probability is roughly the square of the wave function, which obeys some nice wave-like properties. So the way to think about this, to emphasize, is that the thing that has fundamentally particles in quantum mechanics are described by a wave function, which is often denoted by the Greek letter psi, and the wave function is related to the probability that you will detect a particle at a given place, x, and time, t. Good. What else do I want to say about this? Indeed. But quantum mechanics is a very special sort of theory, and in fact, having a theory of the wave function leads to a bunch of sort of counterintuitive properties. What did I want to explain? So, good. The wave function here, the Schrödinger equation, relates the. It's okay if these things don't make much sense to you, but the derivative, it's telling you how the wave function changes as a function of space, where you look, and how it changes as a function of time, and it depends on V here is the potential energy that your system has, where your particle is propagating and what sort of interactions it has. And I want to say something about, I've used the term energy a few times, it came up in questions. So an aside, it's unfortunate that physicists use energy as a technical term when it's quite overloaded in English. We don't have, I'm way behind time, but just to say, I want to disambiguate, I grew up believing that there was some vital energy that I imagined as some sort of flow of some effervescent fluid around the body. No such thing exists, and unfortunately, I think that very often people with some sort of pseudoscientific understanding of how the world works take advantage of the fact that physicists use normal English words as some technical terms to make themselves seem more legitimate, to confuse people into thinking that what they're talking about are the same things that we're talking about. I encourage you to be very skeptical of any let's say alternative healthcare person who tells you that there's some blockage in your energy or something. And indeed, this is also frequently done with quantum. Certainly, the first time the first time I heard the words quantum mechanics, I think were probably by Deepak Chopra, with some very misguided understanding of how what quantum mechanics really is. And indeed, that's part of why I'm not going to do much math, but every once in a while I would like to display some equations, because it's not just the words. Really, the language of physics is mathematics, and it's the mathematics that is precise. English is very useful, of course, but it's not as easy to communicate things precisely, whereas there really is both qualitative and quantitative precision in the physics that we do. Okay, but an actual aside, let me just say what energy is. It's a property of physical systems, a property like we were talking about. There is not some separate energy thing. It's a property of particles or of whatever macroscopic physical system you like. In classical mechanics, you can break it down into kinetic energy, the energy of things that are moving, and potential energy, energy of things that are interacting either gravitationally or electrically. And really, at some deep level, there is some fundamental breakdown of energy into kinetic and potential parts, but it can be useful. I'm not going to insist we only talk about kinetic and potential energy. It can be useful to assign different labels. One source of potential energy is rest mass energy. We'll talk about more next week. This is Einstein's famous E equals mc squared. And of course, you can have you can have energy in chemical bonds, in gravitational fields, in thermal motion, lots of such things. Okay. In light of the time, maybe I'll just very roughly skip this. Indeed, you can very easily solve the Schrodinger equation with a single particle in the absence of anything else. You find just a propagating wave like you'd expect. Let me say briefly about quantum mechanical uncertainty. Now, uncertainty is something indeed people are often confused about. There is this famous Heisenberg's uncertainty principle that you, So Heisenberg's uncertainty principle tells you for a quantum mechanical particle, there is some lower bound on how precisely you can know the position, the position and the momentum of some particle. Now this seems very abstract, but really it's coming from the fact that in quantum mechanics, everything obeys some wave-like motion. And it's just a property of waves. Let me, in a slightly different language, I won't fully make that connection, but if I have some wave that isn't periodic, some a wave like you might see in the ocean, maybe it's traveling some speed. So this clearly has a very well-defined position. It's going to change over time. But it does not have a well-defined wavelength because it's not really a periodic phenomenon. Whereas on the other extreme, if I have some wave that, imagine this going for infinity, just some really periodic wave, then now there's some very well-defined wavelength, but it doesn't make sense to talk about the position of this wave. The wave, this extends as a really periodic phenomenon. This extends in both directions. And so uncertainty, quantum mechanical uncertainty, this uncertainty principle, the idea that there are variables, pairs of variables, which you can't measure precisely both at the same time, really just comes down to properties of waves, right? You can imagine some intermediate, I can draw some intermediate wave, maybe. Okay, it doesn't matter. So this is sort of good. This is less localized than this very local wave. It has some sort of position, but not as precise a position as this very local wave. And likewise, it's sort of periodic. It has, you can talk about a wavelength in some sense, but not really a truly periodic phenomenon. So the big idea of uncertainty relations in quantum mechanics, the idea that no longer can you measure precisely everything you might have thought about measuring in classical physics, really just comes down to the behavior of waves. If you've heard the term, the property of the Fourier transform, we can talk about later. So nothing mysterious, and I want to emphasize that this is really a property of the universe. People get confused about quantum mechanical uncertainty. Am I saying just, we aren't smart enough to measure both position and momentum or position and wavelength? No, it's really a fundamental property of the universe, of quantum mechanical systems, because all quantum mechanical objects have this wave behavior, that there is no well-defined, you can have variables where they're mutually they are not precisely well-defined, right? So the physical system does not have a precise position and momentum at the same time. Good. All right. Let me. I don't have too much, but I wanted just to explain. We started off with the structure of matter, being confused about how the atom works. This classical picture. If it's a quick question.
Yes, it's a quick question.
Okay.
Okay. Schrodinger's equation is a field equation relating, am I correct, the dimensions and time. Where does the field, where do the wave business work into this equation?
Good. I'm not sure I'd say it's a field equation, but in any case, the wave is what we're solving for. Indeed, and so this is a sort of specific form of the Schrodinger equation. I can go more generally. So indeed, these derivatives, physicists very often write down differential equations. The language of nature seems to be differential equations. Indeed, they're telling you about how things vary over space and time, but that's what you're solving for. This wave function psi is the fundamental description of the quantum mechanical system, and solving this equation tells you about the wave behavior of the particle that psi describes. So indeed, it's a wave equation. It tells you how the wave evolves over space and time. Now, in fact, it's more general than just some propagating wave. You can also use the Schrodinger equation to understand the structure of bound states of hydrogen. So, good. What we're going to do, what we do here is we look for a solution to the Schrodinger equation that doesn't change with time. I want to understand the structure of a hydrogen atom, how the proton and the electron interact. I want to find a solution where they're not, moving, but rather where they stay stably as an atom over time. That's the same as having some fixed energy. And you write down the Schrodinger equation using, indeed, this classical equation for the potential, which is closely related to the electric force between the electron and the proton. But you find that for the Schrodinger equation describing the interaction between the electron and the proton, rather than in free space where you can have a particle that's roughly anywhere with any position, any momentum, you find here that there are only a discrete number of solutions to this equation. There are only a discrete number of energy levels, of stable configurations of the electron and the proton. I'm plotting here the potential energy and finding only some discrete energy levels that are allowed. And this is part of why we have the quantum in quantum mechanics. Your very rough picture can be that you find a lowest energy state where the electron is some average distance from the proton. This is the Bohr radius that I erased already. But you find a discretum of excited states, where the average distance between the proton and the electron is different, okay? And you can understand precisely the differences in energy between these different states, and you can understand transitions between them. So, good. If you have a hydrogen atom in, say, the ground state, the electron is relatively close to the proton. With a specific amount of energy, you can excite it to this first state, or even if you have enough energy, you can pull it away from the proton. What do I want to say here? So this explains the photoelectric effect, in that if you send in an individual photon, an individual particle of light, either it has enough energy in order to excite the electron all the way from the ground state to being separate from the proton, or it does not, depending on the wavelength of the photon. And let me briefly show you, apart from my cartoons, we can really understand precisely the real thing. These are different energy levels for where you might, the probability of finding an electron in different places around a proton. And there's some intricate structure. I was drawing the sort of lowest line energy levels, which are spherically symmetric, but in general you can have some non-zero angular momentum as well. But it's something we can understand very precisely. I just want, we can maybe talk about this more offline or next week. I just wanted to emphasize what's been going on. I haven't gone over the topic in depth, but of course, what was going on in these double slit experiments is we were measuring the position of an electron or a photon after it passes through some slit. And I just wanted to emphasize that another place where we're often not as careful with language as we should be, measurement here really just means some interaction with a complex system. And there are still some underlying mysteries about exactly how the process of measurement works in quantum mechanics, but definitely it does not have to do with human consciousness. It does not have to do with you looking at it at something yourself, measurements occur all the time out in the universe. You have quantum mechanical particles that sort of are propagating as quantum mechanical waves and are measured by whatever system they're interacting with and display some particle behavior. Okay, in light of the time, let me just briefly say that this is really how all of our eyes work, right? So, good, we already talked about sound waves, one way in which we are able to get some information from the outside world based on some very complex organs in our heads that have evolved over hundreds of millions of years. In fact, many, I'm anthropomorphizing a bit, but many creatures many organisms have realized, evolution has realized, that is, many times, in many different ways, that there is additionally information in terms of photons, in terms of light, all around us. And indeed, we have these fantastic organs, they have these complicated molecules. There's a picture of a cone. It really, our eyes are very advanced. They work in some very advanced ways. But at the end of it, what's happening is that a photon a particle of light comes into your eyes, interacts with a particular chemical in one of these cone cells. In general, they're called opsins. It transfers between, it causes some excitation in this particular molecule between one quantum mechanical energy level and another. And our brains, in this fantastic visual system that we have, our brains have learned that if we have these molecules which are sensitive only to a particular band of light, rather than undergoing this change no matter what the frequency of the photon is, we have different ones that get excited for different frequencies, wavelengths of photons. And so our brains have learned to take advantage of this quantum mechanical and chemical behavior to parse out the color of light incoming, incident upon our eyes, and create for us the stunning visual effects that we observe in our everyday lives. Indeed, in some sense, of course, in some sense, I know these things are very abstract. We're talking about the structure of matter on incredibly tiny scales, but really, these are the way that our bodies work. So I think there's something very, very cool about being able to understand these principles at the smallest scales. Okay. Sorry for going over, and even with that, I had to skip a bunch of things I wanted to say. Next time, we're going to continue zooming down. Here we were at 10 to the minus 10. Now we're going to go down to something like 10 to the minus 15 next time, talk about nuclear physics. And I've been talking about quantum mechanics. I think we will have to confront because it's something I like and think about, I think we will confront some amount of quantum field theory. And I hope you'll join me next time as well. Thank you.